in this particular case, let's see if we can figure out how one might convert this starting ester, ethyl propionate, into the following product. This ketone shown here. And if we look at the structure of ethyl propionate and we look at the structure of this ketone, we might recognize a correspondence between this portion of the molecule and this portion right here. And that might prompt us to think about the acetoacetic ester synthesis. It's going to be a little bit different than that. So let me just give you as a hint that let's try to proceed via an acetoacetic ester like synthesis. So maybe try to do some retrosynthetic analysis in that regard and then come back to the video and let's see how we should proceed. If I look at this particular compound, I could imagine that it might be prepared from a corresponding material of this type. So if I have this beta keto ester and I have the enolate, which should be fairly easily prepared, and if I were to alkylate that enolate, that would allow me to introduce this ethyl group. So I would need ethyl bromide, perhaps, to incorporate the 2 additional carbons. And then this particular beta keto ester enolate would come from the corresponding beta keto ester. So this compound here is a beta keto ester. So the next part of this problem is remembering the ester that we wanted to start with, namely ethyl propionate, and looking at this beta keto ester, and remembering that a beta keto ester type of structure should remind us of a particular process. How might we prepare this beta keto ester in a way that lets us work back to our desired starting material, namely ethyl propionate? So the question is, first of all, if we're trying to make a beta keto ester, what type of reaction does that remind us of? A beta keto ester should make us think about the Claisen condensation. So let's do a retrosynthetic analysis of this particular beta keto ester in terms of the Claisen condensation. What is the key bond disconnection for a Claisen condensation in the retrosynthetic sense? Here's the carbon that's alpha to the ester carbonyl. Here's the carbon that's beta to the ester carbonyl. So the disconnection would take place between alpha and beta. And that would take us back to the need for one ester unit here. That's the ester to which the enolate is going to add. And then these carbons over here would be part of this enolate. And notice that this enolate is actually just the enolate of the ethyl propionate itself. So this enolate corresponds to this ester in its deprotonated form. So this would be a retrosynthetic analysis based on an acetoacetic ester-like synthesis type approach. The new thing here is that this methyl group right here is already built in to our starting beta ketoester by virtue of the fact that we did a Claisen condensation of ethyl propionate. So after I get a chance to erase the board, we'll go ahead and work this through in the forward sense. Let's begin the synthesis in the forward direction. Recall that our starting material was going to be this ester, and we're going to carry out a Claisen condensation. So we will need a second equivalent of the ester. And in the Claisen condensation, we do want to check for a good Claisen condensation. We should have at least 2 hydrogens at the alpha position of the ester building block, which we do in this particular case. And then we're going to need a base because we're going to make an enolate at the alpha carbon. And then that enolate is going to add into the carbonyl of the other ester. And because we're using an ethyl ester, we should use ethoxide as our base. And then we will use ethanol as our solvent. So remember, you deprotonate, you make the enolate. The new bond is formed between the alpha carbon of one of the ester units and the carbonyl of the other ester unit. We make a tetrahedral intermediate. The tetrahedral intermediate breaks down, and then we end up breaking that bond right there. So the product of this Claisen condensation is the following. Here's the alpha carbon. Let's keep track of what's attached to the alpha carbon. We started out with these 2 hydrogens and a methyl. We still have the methyl group. There it is. And then recall, under these reaction conditions, I'm not working through the mechanism here, but you should be sure that you could write the mechanism if you had to. The product after this initial part of the Claisen condensation is going to take us to this enolate anion. Remember, the deprotonation in the center position is the reaction driving step of the Claisen condensation. And here is my beta carbon of this beta ketoester. And then there's a subsequent step in which we provide a source of protons so that we protonate at that central alpha carbon. And so here is our beta ketoester that we need. We still need to introduce an ethyl group at this central position. So we need to make an enolate again. And then we're going to alkylate that enolate using ethyl bromide. And that's going to take us to this structure. Where now we have both a methyl and an ethyl group at this central alpha carbon. Now we could maybe compress this reaction sequence somewhat. Notice that from the Claisen condensation, we actually generate an enolate at the alpha position, which we then have protonated, and then we have deprotonated again. So in the interest of going by analogy to what we've seen before, I've done it this way. However, one could certainly imagine that once we get to the point where we have this enolate anion in our reaction flask, we could, instead of just quenching with a source of H+, we could add the ethyl bromide directly and perhaps go straight from here over to here. So if we were to use ethyl bromide instead of a protic workup, we might be able to do this in a more efficient way. In any case, once we're here, we're almost done. What we need to do is we need to remove the atoms within this circle here. And so this is the decarboxylation part of the acetoacetic ester-like synthesis that we're doing. So first we are going to saponify. That's going to give us the corresponding carboxylate. And then in order to do the decarboxylation, I need the carboxylic acid. I will acidify the reaction mixture. I'm going to redraw the carboxylic acid in a slightly different orientation to help me see that this is going to be readily decarboxylated. And then in the final step, I will lose carbon dioxide. Maybe we can zoom in a little bit here because I'm going to have to make my structure a little bit smaller. So the decarboxylation, we've lost a molecule of carbon dioxide. I end up with this. This is just the enol form of the final compound that I was trying to prepare. So I'm going to do a little circuitous arrow drawing over here. So let me just come over here, and the final product then, after the tautomerization, is that product there, which was my initial target structure. So just to summarize, I was able to prepare a beta keto ester, at least the beta keto ester enolate here, or after protonation, this beta keto ester. This was prepared via the Claisen condensation, and then I used this beta keto ester in an acetoacetic ester type of synthesis. So I was able to deprotonate at the alpha position in between the carbonyls, alkylate, and then carry out the ester saponification, acidification, and decarboxylation. That's